Hey, welcome back to Math with Patrick. Today's June 27th, and we're solving problem number 178 from the Daily Epsilon calendar. And the answer should be 27, that's today's date. And it looks like the bulk of our problem is going to be here, trying to evaluate this integral. And once we know its value, we can plug it in right there and get 27 for today. And usually with these problems where the bulk of the work is in the first part, I do just like to unravel the kind of easy part so that once we solve for y and we get pi over, it would be pi over x, but since we know that today's date is the 27th, I'm expecting to get pi over 27 for y. Hopefully once we get that at the end of the video, that will be a good enough sign to know that we are correct. So this integral does look really hard. First of all, it's a fraction. Fractions tend to be kind of hard to integrate. Second, we do have some trig functions, and those tend to be tricky as well. I do notice that this integrand is periodic. What I mean by that is that every so often it's going to return to the same value. Cosine, this function right up here and here, usually has a period of 2 pi. It kind of has to do with the fact that when we're on a unit circle and once you rotate 2 pi radians around the circle, we're just going to be repeating our values again for sine and cosine. And this 2, this frequency of 2, kind of just means that we need to divide our period by 2. So the new period of the cosine in the denominator is going to be pi, and then the new period of the cosine in the numerator is going to be 2 pi divided by the 6, or pi over 3. So overall, this integrand is going to repeat itself every pi. So what's kind of interesting is that, our integral goes from 0 to 4 pi, and so it's going to be doing some kind of wavy stuff. I'm not really sure quite yet, but it's a cosine function, so it's probably going to be looking like a wave. And so we're integrating from 0 to 4 pi. However, because of this periodicity of our integrand, I could also just integrate from 0 to pi, because this chunk is going to repeat itself 4 times over. And I think that's going to be my plan. I'm just going to kind of ignore this 4 pi and think of the upper bound as pi, and I'll evaluate something like this instead, just multiplying by 4 in the end. Now, I feel like this problem would be a little bit easier if these things matched. And what I'd like to do to this cosine of 6t is use the cosine triple angle identity to rewrite what this looks like. So I'll do 3 times 2t. That should be obvious. And then there's a triple angle identity where if you have cosine of 3 theta, then you can rewrite it as, let's see, I have it pulled up right here on my phone, cosine of 4 times cosine cubed of theta minus 3 cosine of theta. And all that's happening right here is that theta could be substituted for 2t. And so I'll get 4 times cosine cubed of 2t minus 3 cosine of 2t. Now, for starters, it kind of just looks like I'm complicating things, honestly. And I mean, maybe I am because I'm introducing more terms. But the idea here is I do have cosine of 2t all throughout my integrand. And if I do a little bit more substitution, maybe I'll say like a is equal to cosine of 2t. Then I could rewrite the whole integral as, let's see, integral from 0 to 4 pi. I know earlier I said something about like splitting up the integral, but I'll leave that for later. The numerator, I can replace it with this, and then every time that I see a cosine of 2t, I'll just replace it with an a to kind of simplify the algebraic expression. So I'll get 4a cubed minus 3a. And then in the denominator, I'll get 5 minus, looks like just 3a. And this looks a little bit more approachable to me, though still kind of hard. Also, there's these minus 3a's on the top and bottom. That's kind of interesting. I think what I want to do here is do some polynomial long division so that I can split up my integrand into several different terms. Usually that's a good idea when we have a fractional integrand. So I will put my divisor on the outside, I'll put my dividend on the inside, And then just so it's like easier for me to keep track of my terms, I will say plus 0a squared before the minus 3a. And I will put a plus 0 at the end just to kind of keep track of all my terms. And I am going to swap this around. I will do a negative 3a plus 5 just because I like writing my polynomials in standard form. All right, so this is going to be a little bit messy. I need to multiply 3a by something to get 4a squared, or in other words, 4a cubed. I'll do 4a cubed divided by 3a, and that informs me that I'll put a negative 4/3 a squared as my quadratic term. Multiplying that, I should get exactly a 4a cubed here, and I'll get a minus 20/3 a squared over there. I will subtract away my terms. The idea here with long division is that these terms cancel, and now I have 20/3 a squared minus the 3a. I'll ask once again, how many times does negative 3a go into this? We can answer that using a little bit of division. And of course, the a's cancel. And then I'm left with, looks like negative 20/9a. When I multiply this in, I should get precisely 20/3a squared. Multiplying that by a 5, I'm going to get negative 100/9a. And then subtracting the terms away, these cancel. I should maybe find a common denominator here. Let's see, 100/9 minus 27/9, I believe is the right way to do it. Yeah, because this is the number 3. So I am left with 73/9a. And I think I can go, so can I go one more step? Can I get a linear term for this? I think so, right? I will drop down this 0, so I'll have a plus 0 over here. And then I could say, or I could ask, how many times does negative 3a go into that number? Honestly, kind of hard to think about it that way. I think I'll still just use the division idea here. And looks like all I need to do to find this term is multiply the 9 and the 3 together. So minus 73/27a. Actually, no a right there, right? Because these a's canceled. And I'll just do the arithmetic real quick and get the remainder term as well. Now we can treat all 4 of these terms as different integrals. Also, here is the remainder, and then once you're done with long division, you can always do remainder divided by divisor and tack it on at the end. One thing I don't really like right now is all of these fractions, and I think just to kind of declutter it, I think I will take out the 1/27 from all of these terms and stick it out front. And maybe now is a good time to also stick that 4 there, thinking back to this idea of the periodicity of my integrand. So taking out the 27, I think is going to multiply this 4 by 9. So I'll get negative 36a squared. Then I'll multiply this 20 by 3, so I'll get 60a. This 27 and that 27 match perfectly, so it's just a minus 73. And then as with this 27 here, I'll just do 365 over negative 3a plus 5. And so this a is still cosine of 2t. So when I sub it back in right here, I will get some kind of integral of negative 36 times cosine squared of 2t. And the best way to integrate a cosine squared is to think of a cosine squared identity. You could prove this to yourself by graphing or other trig ways, but we could rewrite it as 1 plus cosine of 2 theta all over 2. And since our theta here is 2t, I will actually get 1 plus cosine of 4t over 2 when I'm subbing in for this cosine squared of 2t. I'll also take this negative 36 out for a sec, just so I can really isolate the fact that I have 1 plus cosine of 4t dt in my integral, at least for this first integral here. Splitting this up would be pretty useful into 2 different integrals. I'll have the negative 36 hang out on the outside. We'll have 1/2 as one of our integrals, and then plus, I'll do 1/2 of, or times cosine of 4t dt. This integral, fairly easy. It just evaluates to 1/2 and then whatever our bounds were, which I believe are still 0 to pi. And then this one, when we have cosine of 4t, we need to think about how sine and cosine interact with integrals, and we also need to think about the chain rule. The antiderivative of cosine is sine, so we'll go sine of 4t. And then for me, what makes sense is that I always imagine, okay, if I take the derivative of sine of 4t, I will get cosine of 4t, but a 4 will pop out for the chain rule. So to counteract that, I do need to apply a 1/4 currently to kind of cancel out the fact that if I took the derivative, the 4 would come out. And so this 1/4 I could combine with the 1/2 that I took out, and so I'll get 1/8 sine of 4t evaluated from 0 to pi. All right, I cleaned it up a little bit. Something that I also did here is I noticed a lot of the terms have a negative sign, so I pulled it out. And here I just took some notes about how we use that power reducing identity to find a linear cosine term instead of a squared cosine term. All right. So actually, I just realized this 1/2 should actually be a 1/2 times t, or a t over 2, because eventually I'm going to evaluate this whole thing from 0 to pi. This integral feels like the nicest next one to target. This one's fairly easy. The integral of a constant is just going to be that constant times your variable of integration. We will then evaluate that from 0 to pi later. For this second integral here, this is just the integral of cosine of 2t, a linear cosine term, not too much of an issue. Just like the last one that we did with the cosine of 4t, we should take the antiderivative of cosine, which is sine, keep our argument the same, and then compensate for the fact that this 2 would need a 1/2 to cancel to get us back to where we started. So the 1/2 and that 60 can combine together. So I will get 30 and then times sine of 2t. And that's going to also be evaluated from 0 to pi. Finally, we're going to need to tackle this fourth integral here on the right. And honestly, this one is a doozy. I don't think I'd be able to solve it like normally. I had to kind of look up an answer and back solve and find this really weird way to prove to myself what this integral is. So, there should be a little dt off to the side here. As I write all these integrals, I should technically have the 0 to pi all throughout, but I'm just going to be a little bit lazy and just have the integral sign for now. The first thing I want to do is replace this cosine of 2t. Earlier, we used a power reducing identity where we know that 1 plus cosine of 2t over 2 is equal to cosine squared of t. But here, I actually want to increase the power for some reason. So to isolate cosine of 2t, I'll multiply both sides by 2. That'll knock out this divide by 2. Oops, I just erased something over here. And then I will subtract both sides by the 1. So now I'll have some expression for cosine of 2t. So I could rewrite my integral as 1 over 3 times 2 cosine squared t minus 1, and then minus the 5. Next, I'll just distribute that 3. So I'll get the integral of 1 over 6 cosine squared t, and then it's a minus 3 minus 5, so might as well just call it minus 8. I also notice now that we have 2 even numbers in the bottom, so might as well factor out a 1/2 and just call this a 3 and a 4. Oops, 3 cosine, there we go. Here's where it gets real funky. I'm going to use the Pythagorean identity here, where I'm going to call this 4 times 1. And 1 is the same thing as sine squared plus cosine squared. So I just have the minus 4 still. I just kind of popped in the number 1 for seemingly no reason. I'll keep the 1 up top. I'll keep the 3 cosine squared t over here, and the 1/2 on the outside of my integral. Distributing this negative 4, I get minus 4 sine squared t on the bottom. And then the minus 4 cosine squared t almost cancels with this 3 cosine squared t. I'm left with just minus 1 cosine squared t on the bottom. I don't really like having negative signs here, so I am going to factor out the negative sign and make these both positive again. Okay, it's still not clear to me, honestly, where to go from here. But again, like I said, I kind of looked ahead, tried some stuff out. Apparently what we should do here is factor out a cosine squared t from both terms in the bottom. So clearly the first one's a 1, and the next one will be 4 times something. And that something should be tangent squared of t. My reasoning here is if we multiplied cosine squared times tangent squared, the cosine in the bottom of tangent would cancel with this cosine here, and we're just left with sine squared. Also, I will move this cosine squared of t into my numerator and call it secant squared of t. That is a reciprocal identity. And maybe you see where I'm going with this now. This is set up to be a great u substitution. If I set u to be equal to 2 tangent of t, maybe you'll notice in the denominator, I'll have 1 plus u squared, because if I square both sides of this, I will get 4 tangent squared of t. I still do have secant squared t in the numerator, and so fortunately, by taking the derivative of both sides of my substitution here, I will get du dt is equal to 2 secant squared t. Treating the differential as a fraction, I know you're not supposed to do that all the time, but I will right now. I'll multiply the dt over to that side, and I'll divide the 2 over to the other side of the equation. This shows me that I can substitute out secant squared t dt for du over 2. So I'll stick the du over here, and my over 2 is just going to kind of be like a 1/2. And I'm going to actually have that 1/2 on the outside of my integral. So I'll have a negative 1/4 on the outside here and a 1 on top. So I perfectly have an arctangent integral here. This integral is just arctan of u. The negative 1/4 is still out here. And then u, I erased it, but u was 2 tangent of t. And so this, well, I guess plus c, is the antiderivative of what we had before. And since we're doing a definite integral, I don't really need this plus c, and it's this that I'm going to use for the integral above. Here's our antiderivative. We have the bounds from 0 to pi. So ideally, what we're going to do is just plug in a pi everywhere, and then plug in a 0 everywhere, and then subtract the two values. But I tried that, and I got a negative number, which should be weird. It should be surprising because we're solving for pi over 12. This should be the value that we're expecting out of this. And I tried it, and I got a negative number, and I thought, well, what gives? Something must be going weird here. And the weird part is that tangent is undefined somewhere on our interval. Specifically, it's when t is equal to pi over 2. That's when this number here turns undefined. It shoots up to infinity, and then right after pi over 2, it comes up from negative infinity. And so for that reason, we need to update the bounds. So let's hop over to Desmos for just a sec. I want to show you kind of the symmetry of our integrand, which would then prove why I'm allowed to do what I'm going to do to our bounds of integration. Here's our function, and like I was saying earlier, it's periodic. So when x, or I guess t technically for a problem, but I'll say x for Desmos, when x is 0 and when x is pi, we have these maxima showing up, and so it does repeat every pi, like I was saying. The period of this function is just pi. And here in the middle is pi over 2, and we just have some kind of local minimum happening here. And fortunately, what I can do is just take the integral from 0 to pi over 2, and then rely on the symmetry of this function to double the areas under these curves, to double what I see over here to what I see over here. So the integral that I'm going to write from 0 to pi over 2 is going to track this positive area, positive area, and a half of this negative area. And then once we double that value, that's going to then add on this part, this part, this part, and that part up until t equals pi. And it's important to do this because tangent comes undefined at pi over 2, and it just kind of broke my bounds of integration. So I'm going to shimmy them around one more time, plug in pi over 2, plug in 0, and hopefully then we're going to get pi over 27. I updated the bounds of integration. They're now 0 to pi over 2 instead of 0 to pi. I doubled this 4 to an 8 to kind of represent the fact that, we're having our interval, but then we need to double it to kind of compensate. So if we plug in pi over 2, plug in 0, do the subtraction, we should get pi over 27. So let's see what happens. The negative 8 over 27 will just kind of stay. The 36 will be right here. And then I'll evaluate each term kind of as I go. So when I plug in a pi over 2 and a 0 here and then divide by 2, it'll kind of look something like this. And ultimately, I'm getting a pi over 4 out of this term right here. Then when I plug in pi over 2 right here, I'm going to get 2 pi. And I know that sine is 0 at 2 pi. It's also 0 when I plug in a 0. So both of these terms are actually just going to 0 out. It's technically a 0 minus 0, but I'll just put a little 0 right there to represent, yep, these terms don't really do anything for my eventual sum. Here I have 30 times sine of 2t. When I plug in pi over 2, I will get sine of pi and sine of 0. Both of these also evaluate to just 0. So fortunately, this term overall is just a 0. Okay, this one's pretty easy. This will just be a 73 over 2t, not t, but pi. And then there's nothing else because if I subtracted, right, plugging in a 0 to right here, I just subtract 73 times 0, which is just 0. Okay, time for seemingly the hardest one. I'll keep the fraction on the outside, and then I'll think about what happens when I plug in pi over 2 and when I plug in 0. Okay, so when I do plug in the pi over 2, that is where I'm going to get an undefined value for tangent of t. Maybe I think for this one, I should probably just be imagining that it's a limit as t is approaching pi over 2, although that's not good enough because tangent has a vertical asymptote where it has different values on either side. I'm hoping that approaching the positive direction, so like from the left, so I guess it would be from the negative side of this value. I think what I want here is a large, very, very large value, essentially a positive infinity out of this argument. So that once I evaluate arctangent of essentially something that's like an infinity, now I'm thinking of the arctangent graph. It looks a little something like this. And I know that it's going to top out at pi over 2. So I'm hoping that pi over 2 is going to be the right number to put here. And when I plug in a 0 into tangent, I get a 0. And then when I plug in a 0 into arctangent, I'm also going to get a 0. So that, I believe, covers all of the kind of plugging in of all the numbers that I need to do. And now it's just time to evaluate everything. Do a little bit of arithmetic. Let's see. So this pi over 4 times 36 will become a 9 pi. That's still a 0. This, I guess, is just 73 halves pi. This one's a little bit weird. I guess I'll call it minus 365 pi over 8. And then all of this is going to be multiplied by a negative 8 over 27. I really don't want to do all this arithmetic myself, so let's just kind of pull out a pi. I will do a little bit of calculator stuff, and I'll let you know what all of these values add up to. All right, what a challenging problem. All of the stuff in the parentheses here evaluate to a negative 1/8. And this is exactly what we wanted, because these 8s cancel, these negatives cancel, and overall, we are indeed just left with pi over 27. So once we plug in y equals pi over 27 into this equation, we do indeed get 27 for x today. So here's my answer. Maybe there's another way to do it, but this is the best I got. So thanks for watching, and I'll see you tomorrow. Bye.